Okay, so my name is Mike Wood, and today I'm going to be talking to you about melt from below, or specifically the role of variations in ocean temperature in the retreat and ice loss from Greenland's glaciers. And to get us started, I'm going to remove all of this text from my title slide here because I wanted to showcase this really incredible picture taken by Josh Willis during one of our ocean surveys around Greenland in 2019. So what we're looking at here is the Greenland ice sheet far off in the background. And here in the foreground, we have the massive Zacharias Strom Glacier. So the ice front that we're looking at, which is visible, is something on the order of about 100 meters, and this glacier extends 600 or 700 meters down into the ocean. And right here in front of the glacier, we see this brown silty water, and this brown silty water is rising out from underneath the glacier, and it's brown because it's melting this is melt water that's coming from deep in the ocean and picking up silt and then rising along the front. And it's this melt process that is going to be kind of the center of my talk today. So a bit about myself. I'm in the NASA postdoctoral program at JPL, and I work with oceanographer Ian Fenty. I did my PhD at UC Irvine, and there I worked with glaciologist Eric Regnault, who's given a talk here in the IGS seminar. And my focus sort of sits somewhere between the expertise of these two gentlemen, namely in the interaction between the ocean and the glaciers in Greenland. And this is in no small coincidence. The start of my PhD is in no small coincidence the start of the Oceans Melting Greenland mission, which began in 2015. So since then, I've been going to Greenland and doing a lot of field work on the margin between the ice and the ocean. I've done a lot of work off boats. As you can, I have a picture of me in the upper left-hand corner in Northwest Greenland, 2015. I've used radar. I worked with the team using a radar interferometer to monitor calving at glaciers in West Greenland. And more recently, I've been involved with NASA's OMG airborne surveys. And here you can see me pictured with the OMG PI Josh Willis this past summer. So we were still able to pull off our ocean surveys in the time of COVID. And this was made possible through the dedicated work of a lot of individuals and a whole string of negative COVID tests. So all of this work and the focus of my research has really been toward the question which I'm going to address in this talk, specifically how do changes in ocean temperature cause the Greenland ice sheet to lose mass? And I'm going to start by providing a little bit of background on past findings of ice-ocean interactions in Greenland and sort of the emerging hypothesis from those initial findings. One, because I know that this is a broad group, this IGS group. We've seen that a lot through all the talks we've had this past year, but also because I think it's pretty incredible how far we've come in our understanding of these processes in just a short amount of time. After that bit of background, I'm going to talk about NASA's Oceans Melting Greenland mission, or OMG, and then show some results of what we've learned from the data from that mission. And then if I have time, hopefully I can get to some comments about the future of the Greenland ice sheet and its interaction with the ocean. So a bit of background. Of course, we care about Greenland because it's the biggest collection of land ice in the Northern Hemisphere. It's got about 3 million cubic kilometers of it, which give or take is about 7.5 meters of sea level if it all melts. Of course, we don't expect it to all melt even in the next century. But we know that it has been contributing substantially to melt over the past, say, 20 years. So if we partition sea level rise since the year 2000, Greenland holds a big piece of not only the eustatic contributions to sea level rise, but really holds a substantial piece of total sea level rise. So to get an understanding of why Greenland is contributing to sea level, we can look at where mass is being lost from the ice sheet. And so this was done in a paper last year in Science by Ben Smith and others, comparing laser altimeter emissions from the recently launched ISAT-2 and in comparison to the first ISAT. And what we see is that really Greenland is losing mass on its periphery. And this is for two main reasons. One is that the edges of the ice sheet are at a lower elevation, so increases in air temperature can contribute more melt in those locations. But it's also because the Greenland ice sheet is not simply a big ice cube sitting on land, but it's a dynamic system of ice where the ice is always on the move. And by observing how fast that ice is moving and where, what we can see is that the ice is moving fastest along the coast. And it's not that it's just moving fastest along the coast, it's that the glaciers in Greenland underwent a large speed up after the year 2000. So if you count up all the discharge from Greenland, it was approximately constant through the 90s until the year 2000. There was a huge stepwise increase in the discharge of ice from Greenland glaciers, and that really hasn't slowed down in recent years. And so here I'm showing results from Mougenot et al. 2019 in Jeremy's PNAS paper. But of course, we've seen independent verification of at least this stepwise behavior from Michaela King and Ken Mankoff, two separate studies that came out just in the past year. So it's this stepwise increase, this faster flow of ice on the periphery of the ice sheet that is helping to draw down a lot of that ice off the periphery. So what is the ocean's role in all of this? Well, we got an initial high profile look at how variations in ocean temperature might be affecting the dynamics of Greenland's ice by David Holland's paper in 2008, which documented this warming along the west coast of Greenland and through Baffin Bay, which happened just prior to the retreat of and collapse of Jakobshavn's ice tongue. So what we really see is starting around 1997, 1998, as that heat was starting to spread, then we have the ice tongue collapse, and then after the ice tongue collapse, then we see a thinning and acceleration of the glacier itself. So this was an indication that small changes in the ocean could have big changes on the ice. So these temperature records from David Holland's paper came from fishermen or that were trawling along the coast, and it was later subsequently reproduced in a high-resolution regional model around Greenland. So I've taken a few snapshots from this simulation, which was produced in the ECHO framework from a paper from Eric Rignot and others in 2012. And what we see is that ocean heat really starts to spread around Greenland in earnest at the turn of the century. So it's important to note that this is a forward model. It doesn't employ any assimilation, but if you compare the forward model results to the observations we do have around Greenland, say in the Labrador Sea, Irminger Sea, or some sparse observations in eastern Baffin Bay, what we find is that it does a pretty good job replicating the general pattern and the magnitude of these temperature changes around Greenland. So in thinking about these changes in ocean temperature around Greenland and the changes in the discharge that we saw, this hypothesis was starting to emerge at how these two things were related. And this was really summarized well in a review paper by Fiamma Stranio and Patrick Heimbach in 2013. Within that review paper, they had this really nice schematic that I'm going to use a lot within this talk. So in the schematic, we have a glacier which is flowing from the interior of the ice sheet on the left to the ocean on the right. And of course, around Greenland, we have this really curious scenario where we have warm water, which is at the bottom of the ocean. So that's the ocean side. On the ice side, we have surface melt on the ice sheet, which finds its way through moulins and channels, gets discharged out from underneath the glacier, and then rises in a fresh plume because it's more buoyant than the water around it. And as it rises, it entrains ocean heat from the bottom of the ocean, and it melts the glacier right at its grounding line. And if this melt is vigorous enough, then you'll see a scenario like I had on my title slide, where you even see an expression of that surface melt, or that submarine melt on the surface of the ocean. So putting this all together, the hypothesis goes something like this. You have an increase in ocean temperature that causes an increase in the glacier melt at depth, and that causes the glaciers to retreat. And once the glaciers are retreating, they're losing ice from their grounding line, which is buttressing ice upstream behind it. The loss of that creates an acceleration and a thinning of the ice, or what we call dynamic mass loss. And of course, adding all that extra ice into the ocean leads to sea level rise. And at this time, we did a pretty good job with either modeling or measuring various components of this hypothesis. For example, the ocean temperature, we could model and measure the changes there, at least on the continental shelf. Glacier melt, I'll get to in 1 second. Glacier retreat, we can see that from space, so we can measure it. The loss of buttressing and the subsequent acceleration and thinning, we could, at that time, could use models to simulate that, and also we had measurements. And then recently, couldn't go through this hypothesis without highlighting Michaela King's paper this year, which really connected strongly the glacier retreat to the acceleration and thinning that we've seen on the ice sheet. So it's this link that, that my research has really been focused on. And if we look at what we knew in 2013, we had one modeling paper, for example, by Xu Yun, who was a graduate student at the University of California, Irvine. And what she did was she ran a high resolution model, the plume in front of a sort of typical Greenland glacier. And she found that the melt there at the grounding line depends very strongly on three main characteristics: the water depth, the subglacial discharge, and the ocean temperature. So with this model of melt, then the question was, can we start to apply that to other glaciers around Greenland? And so we can take, for example, Sverdrup Glacier, which I'm going to talk about as sort of a case study throughout this talk. So if you were considering Sverdrup Glacier, then you could ask, how much is Sverdrup being melted by the ocean? Well, from the modeling study, we know what we need in order to calculate this. We need to know how warm the water is. But for Sverdrup, and really for the vast majority of Greenland glaciers, we had very few CTDs near the glaciers. And what's more is that we couldn't see that warm water from space because it sits on the bottom of the ocean. So if you can't measure it, then you say, well, maybe can we model it? Well, the problem with modeling is that we actually didn't have measurements for most places around Greenland of what the depth of the ocean floor is. And this is really important when you consider the type of water that can get to the glacier, because the warm water, again, sits more than 200 meters below the surface. And this turns out to be a pretty persistent issue around Greenland. So if we look at the International Bathymetric Chart of the Arctic Ocean, which was published in 2012, right around this time, if we look at two places here on the northwest coast of Greenland, the bathymetry in these maps was all put at about 1 to 2 meters below sea level, just simply because we didn't have any measurements there. So even if you were trying to model this, you would not be able to get ocean heat into these glaciers because the shape of the ocean floor wouldn't allow it. So from that standpoint, this link in sort of the grounder hypothesis was really lacking. And it was largely due to the lack of both temperature data and depth data. So enter oceans melting Greenland. So OMG was, or is, I would say, a 5-year NASA EVS-2 mission aimed at answering the question, to what extent is the ocean melting Greenland's ice from below? And to answer this, we've done sort of a full-on scientific strike mission to Greenland, doing bathymetry surveys, both using echo sounders and airborne gravity. We've done conductivity temperature depth measurements, both by boat and by air, really for the entirety of the Greenland coastline, and that started in 2015. And then we've also done surveys of the ice elevation right at the ice front using the GLISN-A radar interferometer. So what has all of this new data given us for Greenland? So these areas that I've shown here in purple on the northwest and southeast coast, these are where we've gone with the boat to map the ocean floor around Greenland. And we've gone in and out of a lot of the fjords there. And this is really vastly revised the way that we see the coastline. So if we compare those 2012 maps to what they look like now, what we see now is that there's an intricate network of these sort of deep submarine channels that allow ocean heat from the continental shelf to actually make its way to the glaciers themselves. So these new maps are the result of the bathymetry surveys by boat, and then a lot of work by Luann, who was a former UC Irvine graduate student and postdoc. And she's done a huge amount of work sort of changing the way that we see this, that we see the Greenland coastline. So as far as the ocean temperature measurements go, everywhere where we've taken the boat, we've also got CTDs. So now within many of the Greenland fjords, we were able to see what the ocean temperature is there, and then at what layers the deep water is sitting. So that was done by boat, and also we've done full surveys by air every single year since 2015, and we're planning to go again for our final year this summer. And all these CTDs are available on the OMG website at jpl.nasa.gov. So those are the ocean observations. The ocean observations and the depth observations will both play into the study I'll talk about next. These elevation observations, which were the final component of OMG, I won't be talking about too much today, but I just wanted to highlight where we have all of these elevation measurements around Greenland for 2016 to 2019, before the time of ISAT-2, and overlapping a little bit, because these are swath-based DEMs, and they just have an incredible amount of detail that I think could support a lot of different studies around Greenland. So this is just one highlight of Helheim Glacier in southeast Greenland. And you can see just the immense amount of detail that are in these DEMs. So I've worked to create a level 3 product of these. It's available on the Physical Oceanography DAC at JPL, and it's in a convenient net CDF format. So really primed for convenient analysis. Okay. So now thinking a little bit about ocean temperature variability and glacier retreat, really thinking about what do we know now about this link between ocean temperature increases and glacier retreat now that we have all this new data. So this is a project that I've worked on over the past several years, both in my PhD and then as a postdoc at JPL. In this project, we were connecting the broad scale changes in temperature. So here I've done some averaging of ocean temperature at around 250 meters all around Greenland. And what we can see is that there was a period of stability in the ocean temperature in the 1990s. Somewhere at the end of the 1990s, that ocean temperature started to increase, and we have this warming period, and that persisted until almost 2010. And then subsequently thereafter, we had a cooling trend, but not sufficiently to bring the ocean temperatures back to what they were in the 1990s. Now, if we compare that to the loss of ice from the front of different glaciers, which I've accumulated here, what we can see is that after we have this warming around Greenland, then we start to see a pickup of retreat and ice removal from the front of the glaciers. So what we're asking here in the study is, how is this ocean temperature related to glacier retreat? What can we learn about it with all this new data that we have? So I'm going to return to Sverdrup Glacier. It's my favorite case study glacier. And so we can ask, what role does ocean warming have in this retreat that we've seen, this 6-kilometer retreat between 2000 and 2017? But it's not just the ocean temperature changes that can have an impact on where the front position is. It's a lot of different components. And so really this changes to sort of a separate question, what processes control the front position of this glacier? And for that, I'm going to return to the nice schematic from Fiamma and Patrick's review paper to do a little illustration. So I'm going to get into the weeds a little bit for Sverdrup Glacier, and I'll sort of talk extensively about it, but then I'll take those results and I'll broaden them out, and we'll look at broader classes of Greenland glaciers based on the same sort of methodology that I'll present here. So looking at, if we're looking at a glacier's evolution through time, really we want to think about what's happening at the grounding line. What will cause the grounding line to move forward or backward? Well, glaciers are always being supplied by a source of ice from the interior of the ice sheet, and in the absence of any other process, that's going to cause the ice sheet to, or the grounding line to move forward. Now, this is being counterbalanced by a couple things. The first is, well, the submarine melt, sort of the main topic of this talk. And that submarine melt is really acting vigorously at the grounding line, and that melt is going to cause the grounding line to move back. Now, it's important to note here, when I'm considering submarine melt, I'm really focused on the melt that's happening there near the grounding line. And because the melt is most vigorous near the grounding line, it's going to act to undercut the glacier and leave some ice seaward of it floating. So when I'm talking about melt from the ocean, some of that includes calving that will occur subsequently, which has been undercut and no longer provides any buttressing to the ice upstream. In addition to ocean melt, the grounding line by definition is the transition between ice which is grounded and ice which is floating. So all of the ice right there at the grounding line is very close to flotation. What that means is if you melt the glacier on its surface, then that could cause some of the ice to unground. And that undergrounding of ice near the grounding line can cause cause the grounding line to shift backward into the ice sheet. So there's an effect from surface thinning here that could be important. And in the same way that undercutting can cause calving by allowing the ice to become near flotation near the front, that there might be some calving associated with that as well. So we have calving associated with undercutting, some calving associated with this ice that's becoming toward flotation. And then we also have another type of calving, which I'll call dry calving, because it doesn't involve any processes necessarily with the ocean. And this calving is the act of the propagation of surface cracks that get all the way down to the ice. And this is typically seen as a rotation of ice blocks that break fully off the front of the glacier. So these ice blocks, before they break off, are fully grounded. So there's a lot of processes going on at the grounding line, and considering them all at once, we can create a mass balance or a flux balance for what's happening at the grounding line. So the change in the grounding line position is a function of the source of ice, the ice which is flowing forward, and then the sinks of ice, which happen from undercutting, surface melt-induced retreat, and dry calving, which I showed in the schematic there. So if we want to understand what the role of undercutting is in all of these processes, it's helpful to create time series of these through time and watch how each of them evolve. So to do that, for the grounding line and position and the ice flow, we can get at that from satellite measurements because we can actually see those processes from space. For undercutting, we're going to use a melt model from Xu Yun in combination with measurements from OMG. I'll talk about that shortly. From surface melt-induced retreat, we can track the hydrostatic balance of ice near the front through time using elevation measurements in comparison to the depth of the bed near the glacier. And then dry calving, since we don't have a way to assess this individually or robustly, we consider this as a residual in this mass balance equation. So what do these look like for Sverdrup Glacier? So I've shown the two pictures in 2000 and 2017 for Sverdrup, but of course you can do front mapping through time, either manually or with fancy machine learning methods or other delineation methods. And what we see for Sverdrup is that up until the year 2000, the ice front was in a pretty stable position. And then after 2000, the glacier underwent sort of a steady retreat of up to 6 kilometers by 2017. So we can also look at the velocity for Sverdrup, again, looking at satellite measurements through time. And what we see is a very similar story in velocity as we saw with retreat, where the velocity is quite consistent until about the year 2000, and then something happens and there's an increase in velocity through time thereafter. So we see a speed up at Sverdrup as it's retreating, which in the absence of any other process, if you saw a speed up at a glacier, then you would expect the grounding line to move forward, but that's actually the opposite of what we saw. So we know that there's other changes going on at the glacier front right at around the year 2000. We can consider that surface melt induced retreat by looking at how grounded the ice is, or how much, what the height of the ice is above flotation. And what we see in the year 2000 is that most of the ice at Sverdrup Glacier was quite high above flotation. And what that means is that if you have surface thinning, then you would have to have a substantial amount of surface thinning to be able to unground that ice and cause a retreat. And that's just not what we saw at Sverdrup Glacier during this time. And we can make the conclusion for Sverdrup that this retreat did not start due to surface melt. That changes a little bit as you get more toward contemporary years. So in 2017, there is ice at the front, which is closer to flotation. And so we do see in just the more recent years at Sverdrup and just the past few, some effect of that flotation, but that wasn't the case when the glacier first started retreating. So we can also consider undercutting, that melt at the grounding line. And for this, we'll use the modeling results of Xu Yun. And so taking this model in a paper that was published by my PhD advisor, Eric Rignot in 2016, Eric took that same modeling that Yun had done and applied it to a variety of different configurations and came up with an equation of undercutting which can apply to various different glacier scenarios. So this is a parameterization of undercutting for different glaciers around Greenland. And before I talk about what the terms of this equation are, it's important to think about what was actually parameterized here in the model. What was parameterized was the maximal rate of melt. And that maximal rate of melt in the model happens just above the seafloor. And so what this rate quantifies is the amount of incision that's happening right at the grounding line, or really the amount of undercutting that's happening on the glacier. And again, I'll just reiterate that if you're considering retreat rates from this process, that also might include some calving that happens subsequently to the glacier being undercut. So how do we calculate this? What goes into this equation? Well, the first thing is the glacier depth. This is where we see the importance of all the multi-beam and airborne gravity that we have around Greenland. So in practice, we sample Matimo Ligum's bed machine map, but this really includes all the information from OMG. For subglacial discharge, we can get at that from regional climate models. And for this study, we use the downscaled RACMO 2.3 P1 regional climate model. And finally, of course, the melting depends on temperature, or in this formulation, it's specifically the ocean temperature relative to its freezing point. And for this, we use a combination of echo simulations and we adjust those to match CTDs, particularly in the fjords where the echo simulations do not resolve circulation. So if we look at the time series of undercutting through time, what we see for Sverdrup is that there was fairly low undercutting in the 90s. We saw an increase in the undercutting rate through the 2000s, and that was because we saw an increase in the ocean temperature. And of course, we see this annual cycle in undercutting, which is the result of large amounts of runoff during the summertime and lower subglacial discharge during the wintertime. So what we see here really is that undercutting is increasing as this glacier is retreating. So if we go back to the mass balance equation, now we've got the left four components. We calculate the right component as the residual. And now we've got time series of all these components through time. And we can start to do interesting things with them, like integrate them through time to see which processes are more important and when. So if I compare, so I've mentioned a little bit that surface melt induced retreat, particularly at Sverdrup, was not a major driver of retreat. So if we integrate undercutting and dry calving, the other two removal processes at the front, we get a picture that looks like this. So this is the area under this curve is the total removal, or I guess the vertical axis is the total removal of ice. And what we see by 2017 is that all of the removal of ice, well, about 4/5 of the removal of ice at Sverdrup was really driven by the calving of icebergs. And in this perspective, ocean melt actually has a very small component of the ice loss. So you might be tempted to ask, is the ocean really affecting this glacier at all when such a small amount of the ice being lost is being done by the ocean? And so we took a little bit different perspective on this, and we considered not what the absolute undercutting rate was, but the anomaly in the undercutting rate. And we did this specifically relative to a time when ocean temperatures were approximately stable and the glaciers were approximately stable. And so we established this baseline period in the 1990s, and we integrated through time what that extra melt or the extra undercutting was. And so this curve gives us a quantity of the extra ice that is being melted away by the ocean. And when we take that extra ice being melted away by the ocean and we compare it to how much the glacier is retreating through time, what we find is that the magnitude of this cumulative undercutting anomaly, it matches quite well with the onset and magnitude of the glacier retreat, particularly at the time when the glacier was really start retreating. Later in the time series, we see some runaway retreat above what our model suggests the undercutting rate should be. And that is a little bit expected because you expect changes in the stress balance and calving as the glacier is undergoing changes. This is providing a lot of evidence that this undercutting has a major role in the retreat. And the acceleration that we see is really a response to this, this progression. So conclusions for Sverdrup, even though the total ablation might occur through calving, its retreat is really initially driven by undercutting, which is related to changes in the ocean. So that retreat is associated with speed up and subsequent mass loss. And so what we conclude for Sverdrup is that the ocean is a really key driver of its changes. So that's one glacier. What about the rest of them? There's over 200 glaciers in Greenland, depending on how you chop it up around different nunataks and everything, and what you count as being connected to the ice sheet. You might get a little different numbers, but we count up 226 of them, and we track their retreat through time and tried to assess in the same way that we did for Sverdrup what the impact of the ocean on these glaciers would be. And all of these results just came out in a recent paper last month, which we published in Science Advances. And so I want to just provide some of the broader conclusions that we've come across based on our analysis of all of these separate glaciers. So for glaciers like Sverdrup, so Sverdrup is sort of in a broader class of glaciers that are terminating in deeper fjords that have access to warm water. So we find that glaciers, if they're in this configuration where they're several hundred meters deep, we know warm water is there. They have a retreat progression and a relationship with undercutting that is very similar to Sverdrup. But that's not always the case. sometimes we find glaciers which have warm water in their fjords, but when the glaciers are terminating on sills or sort of protective constraints within the fjord, we don't find a retreat that is associated with an increase in undercutting. And we think that this is because the undercutting on these glaciers happens on a small floating extension on the glacier that extends out past the sill or the constriction, and this prevents the undercutting from removing the important grounded ice that keeps the ice behind it back. In a sort of similar vein, we find that shallow glaciers really haven't retreated much at all. And when we calculate the undercutting rates using this parameterization that we have on these shallower glaciers, what we find is that there's not been a lot of undercutting, which matches well with the not a lot of retreat that we've seen. And this is because these glaciers are mainly in contact with colder surface waters that aren't influenced as much by the spreading of Atlantic water around Greenland. And finally, there are a few glaciers which have floating extensions in Greenland that we've seen retreat at their grounding line, and these are associated with warm water layers that are also making their way underneath the big floating extensions too. So some of these have broken up in the last 20 years. So like Jakobshavn and Allison, some still persist today, like Peterman and Ryder. So if we put this all together, we formulate these different classes of glaciers, and we try to see which glaciers fit into which class, to try to get at this bigger question of, is the ocean having a big impact on ice loss from Greenland? So when we do this, we find that the deep water ones, which we see this progression similar to Sverdrup, which we can quantify the melt, and we can see that it's having an impact on retreat. About 74 glaciers fit into that category. 51 fit into this calving ridge and cold water scenario, where these glaciers are protected from those warmer layers or from undercutting. And then about 10 fit into this floating extension category. So if you're quick with the math, you realize that this is not at all adding up to the over 200 glaciers in Greenland. And that's because we still have 87 glaciers in Greenland by our count, for which we cannot diagnose the relationship with the ocean because we don't have measurements of the fjord water depth or the ocean temperature there. So while we've done a lot of great work with OMG, and a lot of other folks have been doing a lot of measurements in Greenland, we still have a long way to go. So why are these, this is the distribution of glaciers by type, but if we look instead at the distribution of glaciers by mass loss, what we find is that those 74 glaciers actually account for an outsized component of the mass loss. So these glaciers that are feeling the ocean strongest and retreating as a result of undercutting, those are accounting for about half of Greenland's mass loss. So what we're showing here is that that the ocean is an important player in mass loss, and we might not even be getting the whole story because there could be a lot of a similar story going on with those 87 that are contributing about 20% of the loss. And it's worth pointing out here that these shallow ones, or these protected ones that haven't been retreating a lot, they only account for a very small proportion of total Greenland mass loss. So that sort of concludes the work that we've done in that paper. The main takeaway here is that a spread of ocean heat around Greenland, which really started in earnest at the turn of the century, that caused widespread retreat, and this happened through this undercutting mechanism on Greenland's glaciers. And it's really the biggest glaciers that have the access to the warm water that accounted for more of the loss. And I'll say here in my concluding idea is that we still have a lot of work left to do to understand how the oceans are influencing Greenland's ice. For one, we need to better quantify the transport of heat from the outer ocean to the fjords. So in this study, we relied on CTD measurements that were quite extensive from the OMG campaign. That's not going to be possible every single year. So we really need to get our ocean models up and running to resolve some of the circulation into these fjords, which I think on a Greenland-wide scale just isn't possible yet. I imagine there will be improvements in the undercutting parameterization, or even better if these are included in models and done explicitly. That's going to really improve our ability to assess these processes. And finally, we need more measurements of ocean temperature and depth around Greenland to get at those other 87 glaciers, which we haven't been able to accomplish. Now, if I can check the time real quick. Getting sort of toward the end of my time here, and I had hoped to talk a little bit about the future modeling of Greenland's ice loss in relation to ISMIP-6 and sort of some of the results we have and how they fit into this. But in the keeping time in mind, I'll just keep my focus on a new paper that came out last week by a JPL postdoc named Youngmin Choi. And what Youngmin has done is modeled the evolution of Greenland's glaciers as forced by the same undercutting process that we used in the Science Advances paper. And what Youngmin finds is that when you account for the undercutting in this way, dynamics can account for a much bigger proportion of the mass loss than what we see in the CMIP-6 models. And I think that this is largely still an underestimate, even with the improvements, and that's because many of the glaciers still remain unresolved. So this lack of data in the fjords is not only affecting our ability to understand what's going on with the glaciers now, but it's also influencing our ability to predict how much mass loss is going to come from them in the future. So I would highly recommend checking out Youngmin's paper, hot off the press. So to conclude, the ocean is melting Greenland. We found that with a lot of new data from the Oceans Melting Greenland campaign. And this really happens because of enhanced ice melt that caused the glaciers to start retreating around 2000. We see that ice loss is dominated by glaciers that are undercut by the ocean, but of course we need more data to make further conclusions on that. It wouldn't be a good science talk if we didn't say we needed more data, right? So moving forward, ice models need to continue to make improvements on ice-ocean interactions in Greenland, and then ocean models need to meet them as well by resolving the transport of heat into the fjords. And as a bit of a pipe dream, I'll say that we should also move toward coupling those two. With that, I'll conclude, say thank you, and take questions.
Thank you very much, Mike. Usual procedure for questions, if you could indicate in the chat that you have a question. Paco, go ahead.
Yes, hello. First of all, congratulations on your talk and also on your project. These detailed bathymetry maps that you were showing were really impressive. I have a question. I'm interested in the quantification of the effect on undercutting by warmer ocean temperatures on one side and by increased subglacial discharge resulting from the warming air temperatures. You have focused mostly on the ocean temperatures, but of course there is also the effect that you have mentioned of the subglacial discharge on the submarine melt. And then I would be interested in knowing some more of your ideas on which of these phenomena is influencing more. Of course, this will probably depend on the glacier, for instance, in the case of Sverdrup. And of course, also you mentioned this model by Rignot from 2016, this parameterization. And this could give some clue about this in the sense that you can, they would include both the ocean temperature and also the glacial discharge. But the parameters around and the coefficients were, I I didn't catch the meaning. But anyway, I'm worried for one thing, is that you mentioned that this model is predicting that the maximum melt rate occurs right above the seafloor. However, some other models, more sophisticated models, for instance, based on fjord circulation using MIT GCM or maybe Jenkins Clue model, also predict that the maximum submarine melt occurs higher up on the glacier front. So I'm on the Calvin front. So I don't know how good is this Rignot's model, this parameterization, to be able to give us some insight into the different influence of both the subglacial discharge and the increased ocean temperatures.
Okay, in my response, I'll try to address as much of that as I can. I think the first question was about the which between the increase in ocean temperature and the increase in surface runoff was having a bigger impact on the undercutting rate. And so we've done some back of the envelope calculations using the Rignot model, which you would indicate some of its caveats. And what we find is that the increase in undercutting that we see, it's about 90%. It's about 90% due to the increase in the ocean temperature, and not so much driven by that increase in the surface melt. However, I will say that that once the glacier starts retreating, and you have thinning on the glacier, that thinning process, which I call surface melt induced retreat, that can actually have a very big impact on how much the glacier is retreating. So in our calculations for this, for Helheim, for example, what we found is that the surface melt induced retreat could actually be a pretty, it was a large component of accounting for Helheim Glacier's retreat, more than ocean melt. So that was a pretty surprising result for Helheim. And pardon me for blanking on the rest of the question. Can you remind me what the second component was?
No, I was just wondering you answered the first one, and my second thing was just a concern whether this model by Rignot was suitable for doing such kind of predictions, in the sense that he's also predicting maximum melt rates where some different models, usually more sophisticated, predict that this occurs higher up in the glacier front. Yeah.
So there's a paper out by Dustin Carroll. Maybe this is what the one you're referring to, about where the maximal melt rate is. And in Dustin's paper, what he found was that if the glaciers were big and deep, which is the kind of the main glaciers that we're making these conclusions on using the Rignot model, the maximal melt rate was deeper for those models. So when I say right above the seafloor, I'm talking about maybe 50 to 100 meters. And when you have the incision at that area, the ice below it isn't providing any buttressing at that point, and it can easily break off. And the ice above it also isn't providing any buttressing because it's been undercut. So I think that for the bigger, deeper glaciers, which we're making these conclusions on using the Rignot model, I think we're doing an okay job. For the shallower glaciers, I think that there's a lot of argument, or there could be a lot of argument that maybe that doesn't apply, because in Dustin's work, which we do acknowledge in our paper, he sees some sort of undercutting at the top of or overcutting was the word, at the top of the glacier. But for these glaciers where this overcutting might apply because the maximal melt rate is higher at the top, those glaciers are typically shallower and they're not retreating as much or accounting for much of the mass loss. So I guess in this perspective, when you're thinking about total mass loss from Greenland, I think the Rignot model is a good tool to understand what the role of the ocean is in this.
Okay. Do you remember in which glaciers was that? It was calibrated using some observation data, and these were also for Sverdrup or from
They were in central West Greenland, which is just below kind of the area where Sverdrup is. So I can't remember all of them off the top of my head, but I believe it was Store. Store was the initial model by Xu Yun. And then I think that Eric included Rink Glacier, Kingalusua, and two more, which were in central West Greenland. And this was possible at the time because before OMG, we didn't have a lot of bathymetry measurements in the area. And Eric and some others had done some bathymetry mapping in that region, which allowed the application of these results to other glaciers. So they're all in central West Greenland.
Okay, thank you, and sorry for such long question. Thanks.
I appreciate it. Thank you.
Thank you. Roger, do you want to jump in?
Oh, yes, thanks very much, Tavy. Before the question, my video's on. I raise a glass. Happy birthday.
Thank you.
Thanks very much for that fantastic presentation. I'd almost rather you didn't answer the question I put in the chat about how much the other glaciers are going to contribute to the results you've shown so far. But I wonder if you had thought about how much else they would give. Perhaps a supplementary question, maybe a bit unfair, and maybe for your colleague Choi on the Nature paper, on the timescale that's predicting. I wonder if any account had or even could be taken about changes in ocean circulation patterns, whether or not there would be as much warm water and so on, influencing all the losses.
Yeah, that I think that in general, the topic about feedbacks from extra surface melt, maybe for example, in ocean circulation, I think that is very much in an open question, and something that was not included in Choi's modeling, because his modeling was really I can't remember the ocean projection now, but it's the same one that went into the C6 modeling for an ocean forcing. So it's just a coarse resolution ocean component that has been put forward through time, and I don't think that there's any feedbacks in that from the ice sheet. But it certainly worth investigating. That was the second part. The first part, can you? Oh yes, the 87. Yeah, well, what we've seen is that those glaciers account for about 20% of the mass loss. So they are holding, at least since 1992 until present, a substantial component of the ice that's being lost from Greenland. And if we look at the progressions of retreat and speed up, we see that a good portion of them did start retreating and speeding up at the same time that other glaciers nearby started speeding up and retreating. Which we do connect to the ocean. So there's good reason to believe that a fair amount of them are influenced in the same way, but we didn't have the data to fully assess that.
That's great. Thank you very much indeed. Enjoyed the presentation.
Yep.
I have a question for you actually, Mike.
Yeah.
I'm assuming that Helheim Glacier fits into your category of deep glaciers.
Yes.
Or glaciers in deep fjords. Our observations there suggest that the glacier is carving by propagation of basal crevasses, at least at the moment, propagating upwards and then the backward rotating icebergs, and that undercutting is not a significant, or at least at the time when we made those observations, was not a significant factor. And I just wondered where in your three processes that kind of carving would fit, because it doesn't really seem to be dry carving, but then it doesn't really seem to fit in any other category either.
Well, yeah, so we found the same thing that for Helheim, that there was actually a pretty small influence of the retreat from the undercutting. What we did, somewhat surprisingly, find a big impact from was the surface melt induced retreat, or maybe a better name for it would be surface thinning induced retreat, because we've seen a lot of thinning on Sverdrup Glacier, and that allowed a lot of the ice to become unground from the fjord itself. So in that sort of scenario, if the ice becomes just a flotation, with our results and from what you're saying. So the red arrow, the surface thinning induced retreat, which, sorry, did I lose you? Am I back here? Okay, good. Yeah, so it's the surface thinning induced retreat, which could be either from surface melt or dynamics, is what we saw to be dominant for Sverdrup, or sorry, for Helheim.
Thank you. Are there any other questions for Mike? Oh, I should be checking on Facebook actually as well. Just give me 1 second while I just make sure we haven't got any questions on the Facebook screen. No, just thanks from various people there. So
thank you folks on Facebook, and thanks everyone here for dropping into the seminar today and tuning in. I appreciate it.
Yeah, that promo for the next one.
Oh,
you're right. We have no promo for the next one because the next one is actually somebody who has today been submitting 2 proposals and therefore hasn't had time to make us a slide. And
that'd be Regina.
Yeah, Regina Hawk. So next week, you've all got to come and support Regina Hawk, who has submitted today 2 proposals for funding. So we'll be very, very rich soon. So come next week and make friends with Superstar. I'm not sure that most of us could actually manage 2 proposal submissions in one day, so I think we have to forgive her the title slide. Thank you for the reminder though, Magnus. Okay, I think we're finished up out of questions there, Mike. So thank you very much for a great talk. So
great, thank you all. It's good to see you, and I guess I'll see you all next week.
Thanks very much.